Hello everyone. Welcome to my channel Chemistry by ANR. Today's topic is hybridization. Let us explore the concepts of sp, sp2, sp3 based hybridization and some involving d orbitals as well. Hello everyone. Today's concept is hybridization, and it is a theoretical concept that was introduced by Pauling, which says that atomic orbitals combine to give rise to new set of equivalent orbitals, which is known as hybrid orbital. These hybrid orbitals are like mixture of atomic orbitals, and it is obtained by intermixing of atomic orbitals. You know what? When you prepare a syrup, in that case, what you do in a syrup, you mix the sugar, you mix the water, you mix the syrup of whichever essence you are going to prepare. Now, after making the syrup, the individual component, they lose their own characteristics, and the entire syrup gives rise to a different type of entity. That is what is happening. The atomic orbitals combine and they give rise to a new set of orbital, which is termed as hybrid orbital. And the phenomena, the process of intermixing of atomic orbitals is termed as hybridization. And during hybridization, what happens is the orbitals that are intermixing should not have much difference in energy. And when they intermix, they give rise to hybrid orbitals containing equivalent energies. New set of orbitals that have equivalent energy. Like for example, we say 1s and 1p orbital can intermix to give rise to two set of hybrid orbital, which is sp. 1s and 2p orbital can intermix to give rise to sp2. Likewise, what are the salient features of hybridization? Number one feature says that number of hybrid orbital is equal to the number of atomic orbital that are intermixing. So as many atomic orbitals intermix, that many hybrid orbitals are obtained. The hybrid orbitals have equivalent energy and shape. But always remember that the shape of hybrid orbital may be equivalent, but the electron density is concentrated towards one side of the nucleus, and it has one lobe relatively larger and the other lobe relatively smaller. The hybrid orbitals are more effective in forming stable bonds than pure atomic orbitals. The hybrid orbitals have directional nature because they have a particular orientation in space, and this orientation is actually to minimize the repulsion between the hybrid orbitals. In order to minimize the repulsion, a particular geometry is attained. So the orbitals present in the valence shell of an atom undergo hybridization. And the orbitals undergoing hybridization, they should have almost equal energy. Remember that from a ground state electronic configuration, promotion of electron is not always essential criteria. Electron may get promoted or may not. In general cases, we say most of the cases the electrons get promoted. There may be certain cases where you see in certain examples the electrons are not getting promoted, yet intermixing is taking place. It is also not always necessary to obtain half-filled orbitals in order to undergo hybridization. In some cases, even the filled orbitals of the valence shell, they can undergo hybridization. So the hybrid orbital looks somewhat different. Like I can say one part of the lobe is getting more electron density and the other getting less electron density. This is one hybrid orbital which I am showing you. Like types of hybridization can be sp, can be sp2, sp3 if it involves only s and p. Otherwise, the hybrid orbitals may also involve d orbitals, sp3d and d2 configurations, hybridizations. Okay. So to obtain sp hybridization, plain and simple, we can see that one s orbital and one p orbital, atomic orbital, they intermix to give rise to sp hybrid orbital. And if I say the p orbital is oriented towards the z-axis, then it is intermixing of s orbital and pz orbital. Now here it contains 50% s character and 50% p character in an sp hybrid orbital. And in order to get minimum repulsive interaction, the geometry that is obtained is a linear geometry. So we can say that this is one lobe of sp hybridized orbital on account of the intermixing of one s and one p. So after intermixing of the orbitals, the shape of the lobe gets distorted, and this is what you are getting. Like this, two lobes will be obtained. The other one is this. So you can see it is a linear geometry having a bond angle of 180 degrees in sp hybrid orbital. Example of such molecule is BeCl2, beryllium chloride, where beryllium is the central atom with a ground state electronic configuration of 1s2 2s2 because beryllium has atomic number 4. So 1s2 2s2 in the excited state, what happens is, see, if 2s orbital is having 2 electron and 2p orbital is completely empty, then in the excited state 1 electron from 2s gets transited to a p. So ultimately what happens is this electron is not there and you get 1 electron in 2s and 1 electron in 2p because of this excitation and intermixing of 1s and 1p, preferably a pz, giving rise to sp hybrid orbital. And this is the shape of the orbital, the linear geometry of the orbital. Now, if I say BeCl2, chlorine has one p orbital. So this is the p orbital of chlorine, one Cl, and this is of another Cl. Note that the positive signs are intermixing. That means overlap of the hybrid orbital. So this is your sp hybrid orbital of central atom beryllium, and this is your p orbital of a Cl atom. So this type of overlap is a sigma overlap which is formed by sp and p overlap. So this is known as spp sigma, and on both the sides it is obtained spp sigma. So this is how the orbital overlap of BeCl2 takes place. Next, moving on to sp2 hybridization. Here we can see one s orbital and 2p orbital are intermixing in order to give rise to sp2 hybrid orbital having a trigonal planar geometry with a bond angle of 120 degree. And this is the 3 lobe you can see. This is one lobe. This is the other lobe. and this is the third lobe. Okay, so each hybrid orbital looks somewhat like this after hybridization, and three such lobe is oriented at an angle of 120 degree in order to experience minimum repulsion. This is the orbital overlap of BCl3 molecule, where boron we know is the central atom. And over here we can see that boron has three unpaired electrons. Why? Because the three orbitals, 1, 2s and 2, 2p, they hybridize in order to obtain sp2 hybrid orbital. And the bond angle is 120 degree. So if anyone is telling you that please derive the structure by hybridization, you are going to write boron as atomic number 5 and then write the electronic configuration 1s2, 2s2, 2p1. And then you have to mark that in the excited state, there is an electron transition taking place from a 2s to a 2p. Not always electronic transition takes place, but here it is taking place. So this is 2p. You need to keep in mind how many atoms are combining. 3Cl. Okay, so from this 2s2 configuration, one electron gets transited to the 2p in order to get intermixing of hybrid orbitals, intermixing of atomic orbital in order to give you 1s and 2p hybrid orbital, which is sp2 hybrid orbital. This sp2 hybrid orbital is 3 in number because combining is 1s and 2p. So I can say the 2p orbitals are combining in order to give you 3 set of orbitals, hybrid orbitals, which is sp2. And the bond angle is 120 degree. So this is what we can see. Next is sp3. From here we can see that there is 1s and 3p. Combining atomic orbitals are 4 in number. So there are 4 set of hybrid orbital oriented at an angle of 109 degree 28 minutes or 109.5 degree. It contains 25% S character and 75% P character. In the previous case over here you can see in sp2 hybrid orbital, here it is almost 60-40 case. Okay, but in sp3 here it is 25% to 35% of S and P character. The bond angle is 109 degree 28 minutes. So we can see two cases over here. Once we can see about CH4 neatly. CH4 carbon having 4 unpaired electron in the excited state. Why? Because carbon has atomic number 6. So I can say 1s2 in the ground state electronic configuration, 1s2, 2s2 and 2p2 because atomic number is 6. So here 2s is having 2 unpaired electron, 2p is having single electrons. Here 2p is having 1 electron like this and 2s is having paired electron. There is a transition from s to p giving rise to 1s and 3p, which is sp3 in the excited state. So there are each unpaired electron combines with 1 electron of hydrogen, 1s1 configuration of hydrogen. So you get what? You get 4 sp3 hybrid orbitals, and the lobes are like this. This is one lobe, this is the other lobe, here is the other lobe, and this is the other lobe. It is pointing towards a regular tetrahedron. This is the molecule NH3 having one lone pair. Now, as per the VSEPR theory, we know there is a lone pair to bond pair repulsion for which the expected bond angle, which is 109.5 degree, is reduced to 107 degree and the molecule is distorted and the shape is a pyramid. So, we will say it is a pyramidal geometry. Next, moving on to H2O molecule. Here we can see there are two lone pairs and the oxygen atom is here sp3 hybridized with an expected bond angle of 109.5 degree. And on account of the presence of two lone pair, there is a lone pair repulsion which is greater than the lone pair bond pair repulsion and greater than the bond pair repulsion. So the bond angle is even more reduced to 104.5 degree in H2O molecule. These are the other examples of sp3, sp2 and sp. C2H6 is what? Ethane molecule. It is like this. Carbon-carbon bond. This is 2 and H6 is like this. So CH3 and CH3. It is like this. So each carbon atom is sp3 hybridized. So these are the lobes. These are the lobes sp3 hybridized, combining, overlapping with 1s of hydrogen. 1s of hydrogen like this. So this sigma overlap is what type? It is sp3s sigma. sp3 hybrid orbital of carbon overlapping in a head-on manner with s orbital or 1s orbital of hydrogen. In case of C2H4, it is what? C2H4 is like this. It is like this. It is ethene molecule. So in case of ethane molecule, all were sigma. But here you have like this. It is what? sp2 hybridized. And it has one pi overlap like this. Sigma overlap plane के ऊपर, pi overlap is like this. This is the pi overlap. So ethene is C double bonded C with two hydrogen like this. And you count the number of sigma bond. Here there is 1, 2 and 3 sigma bond because the other is a pi bond. So sp2 where you have 1s and 2p giving rise to 3 hybrid orbital. Always count the number of sigma bond and tally with the number of hybrid orbital or the number of combining atomic orbitals in order to see the state of hybridization. sp2 hybridized carbon can never form a triple bond. It will always form a double bond. So here is the pi overlap and this is sigma, sigma, sigma. Here so many sigma bonds are obtained and this sigma which I am talking about, this is sp2 sigma which is obtained by the overlap of sp2 hybridized orbitals of the carbon, and with hydrogen is sp2s sigma which is obtained by the sigma overlap of sp2 hybrid orbital of carbon to 1s orbital of hydrogen. This is how you obtain the structure. This is the sigma plane and this is the pi overlap like a banana bond above and below the plane, sigma plane. Now next you have C2H2 acetylene structure, C triple bonded C with single bond H over here. Now each bond is actually here, each carbon atom is sp hybridized. How do I know? Count the number of sigma. This is 1 sigma. This is 1 sigma. So 1 and 2. So pi 1, pi 2. Whenever there is a multiple bond, the one bond is always sigma, rest is pi. So it is a triple bond. I will say 1 sigma, rest is pi. So total, each carbon atom, don't see 2 carbon atom. Each carbon atom forms how many sigma bond? It forms 2 sigma bond. So obviously 2 atomic orbitals are combining in order to give rise to 2 set of hybrid orbital, and that is sp hybrid orbital with a bond angle of 180 degree. So this is the orbital structure you can see. This is a bond angle of 180 degree and this sigma bond which is obtained is between sp hybrid orbital. So this is sp sigma and this sigma overlap is sp s sigma with sp hybridized orbital of carbon to s orbital, 1s orbital of hydrogen, and these are the pi 1 and the pi 2 overlap. So this is the plane. I can say that above the sigma plane and below the sigma plane there is overlap. Okay, so there are two types of overlap, above and below the sigma plane. So if I say this is sp hybrid orbital of carbon, okay, and this is the other sp hybrid orbital of carbon. So this is one sp of one carbon, this is of the other carbon. So this is your sigma overlap, and this is the hydrogen sigma overlap on both the side. Now how will you show the pi overlap? This is 1 pi, okay, so this is 1 pi 1, always parallelly you have to draw, and this is another pi overlap, that is your pi 2, again parallel lateral overlap. So this is how you are going to show the orbital diagram. Now over here you can see hybridization of elements involving d orbitals. So d orbitals may square planar geometry. We can see over here 1s, 2p and d. Okay, so dsp2 is a square planar geometry. sp3d is a trigonal bipyramidal, 1s, 3p, 1d. So combining atomic orbitals are 5. Here again 1d, 1s and 2p. Combining atomic orbitals are 4. Square pyramidal, 1s, 3p and 2d. Combining atomic orbitals are 6. And octahedral, 1s, 3p and 2d. Combining atomic orbitals are 6. So in case of PCl5, you have sp3d hybridization. In PCl5 molecule, we can see central atom is phosphorus and the ground state electronic configuration. Here we can see the valence shell. Okay, so in valence shell we can see 3s2, 3p3 configuration, and there are 5 Cl. So here you are seeing, yes, we are getting 5 unpaired electron in the excited state. From 3s to the 3d, 1 electron is getting transmitted and we are getting sp3d. So this is sp3d hybrid orbital. And chlorine gives 1 electron for hybridization, for formation of the sigma bond, rather I'll say. So here this is the structure, TBP structure. So always remember that you count the number of sigma bond and see what hybridization you are obtaining. And if you have to derive the hybridization, derive it from writing the electronic configuration of the central atom in the ground state of the valence shell, and then draw or write the excited state electronic configuration. See how many surrounding atoms are there, how many electrons the surrounding atoms are actually giving for bonding. And then you judge the hybridization. Like PCl5, it is forming 5 sigma bond. 5 sigma bond means 1s, 3p and d. So sp3d. That is trigonal bipyramidal. Now you may think that a tetrahedral geometry is also there. That also has 4. But a square planar has also hybridization type with combining atomic orbital 4. Now remember, in a square planar geometry, there is involvement of d orbital. And this d orbital is always n-1d. Inner d orbital. If it is inner d orbital, then it is n-1d. Combination of ns and combination of np or np2. That gives rise to dsp2. Square pyramidal is sp3d2, and square pyramidal is also, octahedral is also sp3d2. So remember that here you have to see whether there is a lone pair or not. If there is a lone pair, the geometry will be distorted. So you can see PCl5 for sp3d, you can see SF6 for sp3d2. Now here the sulfur atom ground state electronic configuration is 3s2 and 3p4 configuration, but here 6 fluorine, so you need 6 unpaired electron, and here it is happening in that manner. So what will happen? The electron gets transited in this manner, and so you get sp3d2 configuration. This is a part of hybridization from another resource. So there is no harm researching from various resources. So let us see covalency of an element. What is that? Is equal to the number of half-filled orbitals present in the valence shell of its atoms. That means, see, carbon has atomic number 6. So 1s2, 2s2, 2p2, and here it has been shown 2px1 and 2py1. So here we can see that it has a covalency of 4. How? When there is a transition in the excited state from 2s to 2pz, because this is the valence shell of carbon. Now here beryllium, again also same thing. I am seeing here 2s2 and 2p0. So when it hybridizes, there can be electron transfer from 2s to 2p. Now it is not always necessary that there will be only unpaired electrons in order to undergo hybridization. That we have seen before also. So this is what I was talking about. Just see, 2s is having 1, 2p is having 3. So 4 half-filled orbitals. Here again from 2s to 2p. So 3 half-filled orbitals for boron, and for beryllium we are having 2 half-filled orbitals. Okay. So how come 2 half-filled orbitals? 2s is half-filled. 2p is also partially filled. So it is half-filled orbital, means it's not completely filled. Okay. So next, the energy required for excitation is compensated by the energy released during the bond formation. You need energy in order to obtain the excited state electronic configuration, in order to move the electron from one orbital to the other, from one subshell to the other. And this is compensated by the release of energy during the bond formation. Carbon uses its 4 half-filled orbitals for axial overlap with 1s of 4 different hydrogen. So we have seen CH4, we have seen H2O, all these things. We have seen NH3 in the previous section where NCERT textbook is being explained. Now, here again we can see that atomic orbitals, they intermix in order to give rise to equivalent orbitals having comparable energy, and they are known as hybrid orbital or hybridized orbital. And it is the process of intermixing of atomic orbitals of slightly different energy of atom, or you can say redistribution of the energy in order to form new set of equivalent energy orbitals or hybrid orbitals containing identical shape. Like if I say sp, 1s and 1p gives you sp. So here sp hybrid orbital, how many will I get? I will get 2 such, because 1s and another p is combining. Now if I say sp2, 1s and 2p, so hybrid orbital I will get 3. If I say sp3, so 1s and 3p will give hybrid orbital equal to 4. Now I gave you the example of formation of syrup. It is like this. See, mixing of a white paint to red paint in order to obtain a totally different color, that is pink. Okay, so if you take 2 types, you are getting 2 bottles of pink color. So as many atomic orbitals are combining, that many hybrid orbitals are getting formed. This is just a comparison in order to link the concept to hybridization. Now, salient features of hybridization. I will try and avoid repetition. Only it's a revision. Let us see that orbitals taking part in hybridization, they should have comparable energy or small difference of energy. And and the hybrid orbitals are having identical shape, equivalent energy. Number of hybrid orbital is equal to the number of atomic orbitals combining, taking part in hybridization. Both half-filled as well as completely filled orbital can undergo, of course, of the valence shell, can take part in hybridization. Here you can see that the hybrid orbital have actually different electron density. One lobe is a bit having larger area than the other lobe. So the electron density is greater in this part and lower in the other. So hybrid orbital can form stronger bond, of course, as compared to unhybridized atomic orbitals. The hybrid orbitals have directional character, and I told you that they are oriented in such a manner in order to experience minimum repulsive interaction and maximum stability. So these are the types of hybridization that we will discuss. Many more are there. This is sp3 hybrid orbital, 1s and 3p. Let us see that. This is 1s orbital, px, py, pz combining. So I'm having 1, 2, 3, 4 atomic orbitals combining in order to get 4 set of hybrid orbital. Now this is 1, this is 2, and this is 3, and this is 4. So these 4 set of hybrid orbital, they orient in space in such a manner in order to experience less repulsive or minimum repulsive interaction. And so the bond angle is 109 degree 28 minutes or 109.5 degree. Now here we can see it is a tetrahedral hybridization or tetrahedral geometry. Shape is tetrahedral. Here we can see it is occurring in methane, where the central atom is carbon. Carbon is the central atom. Ground state electronic configuration. Here 2s is having 2 electron, 2p is having 2 electron. On promotion of the electron from 1 2s, it goes to the 2p, and here I am having 2s1 and 2p3. So when they intermix, what happens is S and 3p intermixes in order to obtain sp3 hybrid orbital, and all are similar in energy as well as shape. So this is a tetrahedral geometry, and it almost it forms a regular tetrahedron. Keep in mind that here all are sigma bonds. Next, moving on to ethane. Here again, this type of example I have shown you. This is one carbon, this is the other carbon, and here there are 3 hydrogen each. Now, each carbon is sp3 hybridized. Derivation remains the same as the previous for methane. So for sp3, we have 4 lobes, 1, 2, 3, and 4 hybrid. So this type of sigma overlap is known as sp3 sigma, and these are sp3 s sigma bond formation, and all are sigma bond. Okay, so moving on to NH3 that we have already discussed. Let us see, there is one lone pair. State of hybridization is sp3 on account of lone pair bond pair repulsion, which is greater than the bond pair repulsion. There is a net contraction in the bond angle, and it is less than 109.5, or it's actually 107 degree, which is less than 109.5, which is expected for a tetrahedral geometry. Now we can see the shape is pyramidal, because seeing the shape, we will just see the bond pairs. We are not going to see the lone pair. Formation of H2O, again the same thing. Oxygen atom is the central over here. You can see it is having 2s2 and 2p4 configuration, and there is what is happening here. There is in excited state, it is like this sp3 type of electronic configuration, or rather I'll say sp3 hybridization, of course. Now this 2s and 3p undergoes hybridization. Now this 2 hydrogen will be actually pairing up with the 2 lone pairs and forming this type of sigma overlap, which is sp3s sigma overlap. And there are two lone pairs remaining. These are the two lone pairs. The lone pair repulsion is of course greater than the lone bond pair repulsion, which is greater than the bond pair repulsion, for which here the bond angle is even lower than that of ammonia, and so it is less than 109.5 degree also, which is expected for a tetrahedral geometry. Moving on to sp2, 1s and 2p orbitals undergo intermixing to form three set of hybrid orbital, which is having a trigonal planar geometry with a bond angle of 120 degree. So this is trigonal hybridization. Bond angle is 120 degree. So these examples are boron trifluoride. Here the ground state electronic configuration is 2s2, 2p1, because n is equal to 2 is the valence shell over here. Now there is an excitation that takes place from here 2s to 2p, and there are 3 unpaired electrons, and I have 3 fluorine over here that we can see. So it is like this: sp2 hybrid orbital, the 3 fluorine pair up with their electrons in this manner in the excited state. And what is the geometry over here? It is a trigonal planar geometry with this type of sigma overlap, and this overlap is sp2p overlap, sp2p sigma. Why? Because fluorine uses its p orbital, so it is sp2p sigma. How many such is formed? 3 sp2p sigma bond is formed, and this is the bond angle of 120 degree. Now next you move on to ethylene, that is C2H4. I've already showed this type of structure. It is like this with a pi overlap here. This is the pi overlap here, and these rest are the sigma bonds. Now I have also told you one more thing, that in order to predict the hybridization, do count the number of sigma bond. If it is 2 sigma bond, then hybridization is sp. If it is 3 sigma bond, it is sp2. If it is 4 sigma bond, it is sp3. This type of thing you should keep in mind. Okay, so here we can see what is happening in the excited state, and so it is sp2 hybrid state. Not all are utilized, because here you have each carbon is having 2 hydrogen. So now this is unhybridized p orbital, which is actually undergoing pi overlap, lateral overlap. So you can see the orbital picture. It is like this for one carbon. There is another carbon beside, in order to give you this type of orbital diagram. This is a carbon, this is also carbon, and here you have 2H each. So this type of sigma is sp2 sigma, and this type of sigma is sp2s sigma bond. And this is the sigma plane. Pi cloud is oriented above the plane and below the plane like a banana bond. Okay, so this is like this. The bond length, always keep in mind, of a double bond is lower, bond order is greater. So carbon-carbon double bond consists of one sp2 sigma. We have seen over there. Bond length is 134 picometer. Now next you can see here sp hybrid orbital. Sp means 1s and 1p undergoing. So there are 2 atomic orbitals intermixing, and this is known as diagonal hybridization also, with a 50% s character and 50% p character. And you are seeing 2 hybrid lobes here. This is one lobe and this is the other lobe, having minimum repulsion at a bond angle of 180 degree. Now this example is beryllium difluoride, yeah, fluoride you can say. Beryllium is the ground state electronic configuration 2s2, valence shell electronic configuration. There is a promotion of 1 electron to 2p, and there are 2 fluorine which gives 1 electron each. So this comes from fluorine. Okay, and here is the orbital diagram. Let us always focus on the orbital diagram. This is BeF2. So let us come over here, BeF2. So boron is having sp hybridization. So this type of sigma overlap is actually sp and p sigma. sp of carbon, p of fluorine. Such sigma is also seen here. Okay, so there are two sp-p sigma bond, right? So this is a linear geometry with a bond angle of 180 degree in order to experience minimum repulsion. Such case is seen in acetylene. Remember in acetylene what I said, that it is sigma bond here, sigma bond here, sigma bond here, but there are two pi bond, pi 1 and pi 2. So each carbon atom is sp hybridized, and to see that, you see each carbon atom is forming two sigma bond. Now carbon has, this is the ground state electronic configuration, this is the excited state electronic configuration. You have one hydrogen each, right? So you are having two unhybridized p orbital which undergoes pi overlap. This is the state of each carbon atom. This is each carbon atom having two sp hybrid orbital, and these are the unhybridized p orbital. Now you see the complete diagram. This is the complete orbital picture. Carbon, this is the complete orbital picture. This is your sigma, and what type of sigma it is? It is sp-sp sigma bond. Now here what do you have for hydrogen? This is also sigma. You have sp-s sigma overlap, and there are two pi interaction. If it is pi 1, the other one is pi 2. It is lateral overlap that you can see. The banana bonds are, this is one and this is the other. Always it will be above and below the sigma plane. One thing keep in mind, you know what? The electronegativity of an atom, it depends on the state of hybridization, you know, because if the S character is greater, then the electronegativity of the atom is also greater. So if a carbon atom is sp hybridized, then electronegativity of that hybrid atom will be greater than sp2, than sp3. The reason is S character decreases in this order. Okay, so now I can say that in case of C triple bonded CH over here, CH triple bonded CH, this carbon is more electronegative than a CH2 double bonded CH2, than a CH3 single bonded CH3, right? So hybridization involving d orbitals, that also we can see over here. If we can involve outer d orbital, I have told you this, if it is outer d orbital, it is a TBP structure sp3d, and it is like this. What do I mean by outer d and inner d? Outer d means it is of ns, np and nd. If I say dsp3, this D is the inner D, and this inner D corresponds to n-1D. And this is also a TBP structure. Only the difference is this has inner D involved and the previous one has outer D involved. The importance of this type of hybridization we will come across in the coordination chemistry chapter. So this is a TBP geometry, and regarding TBP geometry, I have explained in the previous modules as well. Now sp3d2 is octahedral geometry. Again, when I say d2, it is outer d, and if I say d2sp3, that is inner d orbital. Both are having octahedral geometry. dsp2 is a square planar. So this is again inner. When I'm writing D first, it is always n-1D. Okay, so it is inner D. And sp3d3, which rarely we will actually discuss, is pentagonal bipyramidal. Just keep in mind that it is pentagonal bipyramidal. Okay, so regarding sp3d hybrid orbital, see this is 1s, P3 should be there. So 1, 2, 3. And this is your DZ square. When it undergoes hybridization, a TBP structure, sp3d, is obtained in this manner. And regarding TBP structure, if you have to derive PCl5 structure, talk about the central atom phosphorus. You know phosphorus has electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p3. So here the valence shell is 3s. That means n is equal to 3 is the valence shell, and 3s2 and 3p3, 3s2, 3p3. Now I need 5 unpaired electrons because 5 chlorine are there. So here 1 electron from 3s gets transited to 3d and you get 1s, 3p and 1d. So sp3d hybrid orbital. And this is a TBP structure with 3 equatorial bonds which experience minimum repulsion and are more stable. The 2 axial bonds, they experience greater repulsion and are less stable, and on account of greater repulsion, the axial bonds are longer than the equatorial bonds. So if there is in case any lone pair in a geometry in a molecule, it will be having the position at it will be having the position at equatorial. In sp3d2, it's octahedral geometry. You can see s, p3 and d2, dz square and dx square minus y square. Now again, keep in mind, in octahedral geometry, it is like this. Now the equatorial bonds are less stable because the bond angle has decreased, and so it experiences greater repulsion. Now more stable is your axial bonds. Axial is more stable here. But in a TBP structure, what I said is, in a TBP structure, equatorial is a more stable. Axial is a longer bond. Okay, so this is just the opposite for octahedral. If there is a lone pair, it will occupy axial, which is more stable. sp3d3, which I said is actually a rare question to be asked. sp3d3, this is one of the example, IF7. These are certain practice problems. You can give it a try, and they are very good practice questions. Okay. So next, this is something which is a quick mode of finding out what type of hybridization you will get, and these are generally applicable for MCQs, okay, not for elaborate. For elaborate hybridization, you need to write ground state electronic configuration, and you need to write excited state electronic configuration, and you have to see what hybridization it will be. Let us see this quick revision. Find the valence electron of the central atom in the ground state, and that is valence electron, and let it be G. So this is G. Count the number of monovalent groups such as H, Cl, Br. They are having a valency 1. That let be V is monovalent. If the given species is anionic having a negative charge, then it is represented by A. If it is a cation, the charge is represented by C. Now this is how to calculate the number of hybrid orbitals from the knowledge of what? The valence electron of central atom, that is G. And what is V? I said V is how many monovalent atoms are attached. So for simple molecule, it is half of G plus V. For polyatomic anion, half of G plus V, but you need to add this charge over the anion, and for cation you need to subtract the charge over the cation. Now depending on the value of depending on the value of X, if X is equal to 2, it is SP, X is equal to 3, it is SP2, 4 sp3, 5 sp3d, 6 sp3d2 and 7 sp3d3. This is some practical I will say examples being taken where the formula is actually applied. This is neutral simple molecule, so half of G minus V. Anion, so you need to add on the charge 2 minus. This is again simple molecule. This is an ion add-on charge +1, simple molecule, and here it is a cation -1. What is the charge? So depending on the value of x is equal to 3 means sp2. So sp2. X is equal to 4 sp3. So this is the application of the concept. I hope the concept of hybridization from all possible angles, from all possible resources that we have discussed will help you to groom your concept accordingly. Thank you all of you from my end.